And then you guys can ask questions. I'll just take questions. There was one I wanted to talk about. This is sort of like it. All right. Draw the product of that reaction and predict the mechanism.
Did you ask just for the product or the mechanism too?
Yeah, well, yeah, go ahead, the whole thing. Actually, name the mechanism, SN1, SN2, E1, E2, whatever, and draw the mechanism. Okay, so do you have a leaving group? You do? What is it?
Chloron.
Right. So the one thing I wanted to point out with this, I've said it before and you should probably know it. So in these chapter 7 reactions, hydroxide is never going to be a leaving group. More broadly, no strong base will ever be a leaving group. There are some reactions you'll see in Orgo 2 where a strong base can be a leaving group, but it's because they're, like, I don't want to go into it, I just prepare you when you take Orgo 2. You might see hydroxide be a leaving group, but it's from a much more reactive position, right? So you make a molecule that is way more reactive than any of these, and so because it's so reactive, it can kick out something that's also pretty reactive. So here, in these reactions, hydroxide won't be a leaving group. If you want that OH to leave, you got 3 choices. Again, this is just a review. So if you use SOCl2, you turn the OH into a chloride. You can use tosyl chloride, that turns the OH to tosylate, or you can use an acid to turn the OH to a water. Okay, those are your three ways to make an OH leave. So OH is not a leaving group in this reaction. It's not going to do anything. Now, so do you have a good nucleophile or a strong base? Got a few shakes, a few nods. All right.
Can I ask a question just really quick?
Yeah.
So if you see like one of those products, or if you see an acid or a CL2, can you just assume that the OH is going to be what leaves in that reaction, or if there's a
If you
leaving-
see this, yeah, so that's the only reaction you guys know with SOCl2, and frankly, you just have to memorize this. Alcohols, like if we treated this molecule, I'll do this and then I'll erase it. Right, so if I treat this molecule with SOCl2, that's what I get.
So if we see those signs, then we can assume even if there is a leaving group present, that it's going to be the OH that does the reaction.
Yeah. So SOCl2 is not a nucleophile. Right. So the book's got the mechanism. I know some of my colleagues teach this mechanism. I think I don't know. Is it better for me to ask you guys to memorize it, or is it better to ask you to learn the mechanism? Those of you that really like mechanism would probably like to know the mechanism. It's in the book. You can study it that way. I think given that this is the first time you guys are going to have to write mechanisms on an exam, I'd like you to focus on just, acid base, SN1, E1, SN2, E2. Those are the mechanisms you're going to have to know. Alkyl migration. This mechanism's a little complicated, but it involves replacing the OH with a chloride and inverting any stereochemistry there. So again, the mechanism for that is in the book if you want to look at it, if that would help you learn, or you can just commit that to memory. The second one, if we did tosylate, second way would be, that's not going to touch the chloride. That will turn the OH into an O-tosyl, and it will leave the stereochemistry the same. Same thing on the mechanism. That mechanism's in the book. And then the third way, this acid is going to be, it's got to be something strong. Sulfuric acid would typically be used. All right, and so you can never have water be a leaving group with a good nucleophile or a strong base, right? Because you can't have a strong base and a strong acid all in the same pot. If I mix sulfuric acid and sodium hydroxide, I'm not going to get my SN1, SN2, whatever. I'm just going to get hydroxide reacting with sulfuric acid. I'll get water and hydrogen sulfate, and everything will just sit there. Okay, so this third one down here can only be used in SN1 and E1 with a weak nucleophile or a weak base. Okay, everybody good on those three things? It's kind of we're getting to the point. You may have noticed things have gotten complicated. Anybody had that conclusion? All right. So we're gotten to a point where there's always little avenues you can chase down. So I want to get back to this question. Most of you look like you were saying there's no strong nucleophile, good nucleophile or strong base. And there is. There's not a strong base. There is a good nucleophile. Sulfurs are good nucleophiles. Remember that nucleophilicity increases as you go down the periodic table. Sulfur's below oxygen. So if you thought OCH3 is a good nucleophile, and you should, then SCH3's got to be a good nucleophile. It's even a better nucleophile. So we've got here, so that sulfur anion is a really good nucleophile. All right, it's not a very good base. It's not a strong base. And so that nucleophile is going to tend to do more SN2 than it will E2. And it's somewhere in your notes or in the lecture, I tried to do it in every, I can put them up again. I've tried to do this in every individual meeting. There's a list of nucleophiles that aren't strong bases. So anything that's a strong base has the potential to be a really good nucleophile, especially if it's small. But there are some nucleophiles like this one that are good nucleophiles without being a strong base. Okay, so this basically says then it's going to be an SN2 reaction. All right, if it can be an SN2, it's going to be an SN2. You've got a polar aprotic solvent that helps SN2 and E2, and the temperature's low, and that tends to favor S over E. Okay, so we're probably going to do an SN2 reaction. So let me stop there. If you didn't do an SN2 reaction, do one. Draw the mechanism. And I'm going to write this list of nucleophiles over here.
Dumb question. What does the CS mean?
The CS would be helpful. I was trying to be, I don't like just repeating myself. CS is cesium.
Okay.
So if there were a periodic table in the room, as there should be in every classroom on campus, I've decided, you'd see that. It's a group, like if that was sodium, you'd know what it was. So this is, cesium is just, it's under rubidium, which is under potassium. So it's a group 1 metal, it's just going to be plus. So cesium is going to be plus, that means the sulfur's got to be a minus. You guys should not have the periodic table memorized. I don't have the periodic table memorized. I know did anybody have to memorize the periodic table in high school? Where'd you go?
Village Christian Academy.
It's gotten more rare. So when I started 20 years ago, like most of my students came in and they had this assignment. Some of my friends' kids were like, "How do I memorize the periodic table? You've got a PhD in chemistry. You must have the periodic table memorized." And I was appalled. Like, it's great if you do. It's like knowledge is never going to hurt you, is my opinion. It's always nice to know things. Like the more you can know and the more skills you can have, the better off you are. You may never use it, but like, and the periodic table is amazing. Total aside here. Sorry. Periodic table is amazing. You should know how to use the periodic table, what trends are, how to read it. Like really the discovery and elucidation of the periodic table is an amazing human story. But it's like you put it up in the room, like it's easy to look up. So you shouldn't feel like you have to memorize that. There is a periodic table in Salem 12. So on the exam you'll see one. You should always feel free to consult the periodic table at any point in my class. All right. So if you're working something and you're wondering if it's open book, open note, if I haven't made it explicit, but all you want to look at is the periodic table, look at it. Okay. So I'll stick to lithium, sodium, and potassium from here on out. So cesium plus, sulfur minus. I said this is going to be an SN2. And so the reaction is going to be, what color do we use here? So the nucleophile is going to be sulfur. It's going to displace the chloride. That's your SN2. The SN2 is a concerted nucleophilic attack, leaving group leaving. So the new sulfur carbon bond, this arrow forms that. This arrow forms a CS bond. This arrow not forms, breaks. Right. Every arrow is going to form a bond or break a bond. Yeah.
We don't have to write in form and break, right?
No. That's me
just,
teaching.
Okay, gotcha.
The mechanism is just the arrows.
Okay, that's what I thought.
Yeah.
I just was,
And here, so you might think, well, this does show atomic movement, except a lot of times people will draw the arrow from the chloride. I see this a lot, especially early. Like I said, it's the first time you guys are writing mechanisms on an exam. So, you know, the arrow that you're drawing, you'd be saying, the chloride's leaving, so I need to show an arrow from the chloride going away. The way we interpret a mechanism, this curved arrow starting with the bond shows those electrons going with the chloride. Okay, so the chloride is gaining the 2 electrons it shares with the carbon. Right? A bond is shared electrons. So if those electrons are coming with the chlorine, that bond the bond necessarily has to break. The atom has to move away from the carbon. Right? If the chlorine's no longer sharing electrons with that carbon, there's no bond there. Okay, so let's draw the product we get. And now you get inversion, that's the other thing, you get backside attack on this secondary carbon. Right, so the chlorine is wedged out, sulfur's gonna have to be back. And the main reason I wanted to show this one is that hydroxide stays there. And then if you want, you get cesium chloride as a byproduct. Now, I mean, it's not even really a byproduct, right? It's a product of this reaction, cesium chloride. I'm an organic chemist. You're doing this. If you did this reaction, you'd be doing it in an organic lab. So you care about the organic molecule. So if you don't write cesium chloride on the exam, that's fine. So if you only write this molecule and you draw it like I've drawn it, you'll get full credit. If you only draw cesium chloride, depending on my mood, I might give you a point or 2. If you write cesium chloride along with this one, you'll get full credit. Right? So you got to write the organic bit.
So you'll never ask us to write like the product other than the organic, the main organic.
Right. That, I mean, on if you look on old exams, there's always a sheet of reactions, right? Like draw the product, draw the major product. I probably should pay more attention to it. It's a lot cooler when you do this in the lab. So a lot of times when we do these SN2 reactions, you know, you've got a cesium thiomethoxide salt, and that there's a bit of organicness to it, and so it's soluble in the DMF, and then it's going to turn out that cesium chloride is not very soluble in the DMF. So as this reaction runs, you actually see a precipitate form, which I think is pretty cool. I don't know how you guys feel about lab, but it's always cool when the color changes or a phase changes, some sort of physical change you can look at and be like, something happened there. Like the most boring labs, the most boring chemistry labs are always the one where it's like, here's a white solid and it turns into a white solid. When it was in solution, it was just a clear solution and nothing happened. You know, it's like, you don't see anything. Again, a lot of times you don't see anything in real life chemistry labs, but you're being paid to do it, so it's okay. All right, so that would be the product. It's an SN2 reaction. The arrows are as I've shown.
Can you go over why it's an inversion? Why that happens?
Yeah, I can. Yes, I can. Let me do that first. So. I'm going to draw a pH for this thing. That benzene ring is a phenyl. There's an H there. Okay, so there's, if we look at the chloride that way, if we look at the alpha carbon this way, then the nucleophile is going to come in here. Sulfur actually has 3 lone pairs, but I'm just showing 1. And it is going to attack, it necessarily attacks from the back. And the reason is, the sulfur electrons are going into the carbon-chlorine antibonding orbital. The antibonding orbital exists outside the bond. Right, so the sulfur is sticking some electrons into that antibonding orbital, and that has the effect of breaking the carbon-chlorine bond. And so the carbon is sort of there for a moment, sort of held, it's 5, we call it 5 coordinate. It doesn't have 5 bonds, but there's 5 atoms around it. And at that point, So in the transition state, I'm just showing the atoms, right? So in that transition state, it's 5 coordinate. And a 5 coordinate atom, if you go back and look at Vesper, is going to have 3 in the plane and then 2 poking out, linear. And then this is going to collapse. The chlorine's going to keep leaving. We're going to make that sulfur bond. And you'll get that, and the chloride will be over here gone. And again, the way to judge this, like, if you think about this as an acid-base reaction, a Lewis acid-base reaction, so the Lewis acid is the partial positive carbon, the Lewis base is the sulfur, right, nucleophile, electrophile. So sulfur minus versus chloride minus, which one of those is a weaker base? And it turns out chloride is a weaker base than sulfur. So this is going to act like a Lewis acid-base reaction where the side that's favored is going to be the side that's more stable. That chloride is the easiest. It's hard to judge the stability of this molecule versus this molecule. You can. The carbon-sulfur bond turns out to be a lot stronger than the carbon-chlorine bond. But if you just look at the bases, the sulfur minus is a stronger base than the chloride minus, so the right is favored. You get, and the inversion, again, is because the nucleophile has to come from directly opposite the chlorine and make this bond. And so it's not going to be able to bond and have all 4 atoms this way. So basically that tetrahedral carbon has to sort of pop open like an umbrella.
Could it ever not cause an inversion in an SN2?
No. And so this is actually this is important enough, I'm going to check that I'm still recording. 6 minutes. Okay, so every SN2 reaction gives you an inversion. Every pure SN1 reaction gives racemization, right? So if I have one molecule do an SN1, obviously I can't get 50-50. Even if I had 6 molecules, right? If you've ever flipped a coin 6 times, 10 times, right? You rarely, not rarely I should say, but you often don't get 5. If I flip a coin 10 times, I can get 6, I can get 4, I can get 3 or 70. I once actually flipped a coin 10 times in a row. This is what we did before we had the internet. We just sat around flipping coins. Now this was I don't know, did you do that in a high school math or stats class? Like, knowing what I know now, the teacher was bored and didn't want to work that day, didn't prepare a lesson plan. So he gave all of us a quarter and told us to flip coins and count it. And we were 12. Worked out pretty well. Anyway, so if you have one molecule, right, SN1 is either going to give inversion or retention. The leaving group leaves, you get a planar cation, and then the nucleophile comes in, top, bottom, left, right. It's all equally possible. If you only have one molecule, though, it's got to be one of those. It can't be all of them. But we never have that. So statistics, again, if you've studied some statistics really require a very large sample. And they require samples large enough that we rarely actually have them apply. Like I've talked to people who curve their classes, colleagues who curve their classes. That, like, I have 58 students this semester. Even if if you're all together, that's not nearly enough. And you're actually divided into 2 sections. Like right now, there's 10 of us. No statistics will apply here. Okay? It would not be weird if we were all left-handed. It wouldn't be weird if we were all from Montana. I mean, like, you get really weird things with small sample sizes. So just remember that when you see human studies, right? The population's never large enough. For molecules, though, right, statistics were made for molecules. On this board, it looks like I've got one molecule on the left reacting with one cesium thiomethoxide, giving one product. In reality, I've got like 10 to the 23rd of these. I've got maybe 10 to the 24th of these. I'm going to end up with 10 to the 23rd of these. Like enormous numbers that we can't even really fathom. Statistics work perfectly. So if you do an SN1 reaction where the leaving group leaves, and you get a planar carbocation, you're going to see 50-50 R and S. Doing an SN2, if this is purely an SN2 reaction, right? Every sulfur kicks out the chloride in a concerted process, then every one of those alpha carbons inverts. So if we had, 90% EE here, we would have 90% EE here. If it's SN2. We would have 0% if it was SN1. Now, also in reality, to look a little deeper at that, if we really went into the lab and did this reaction, we might actually see like 84% EE. There's no way you could predict that. You can predict 90%. You can say this is going to be an SN2 reaction. We got a really good nucleophile. We got a polar aprotic solvent. Temperature's low. It'll be SN2. If it's SN2, whatever the optical purity of the starting material is, stays in the product. If you look at this and say we got a crappy nucleophile, we got a protic solvent, it's going to be SN1. If it's purely SN1, it'll be 0%. You can predict 90 and 0. You couldn't predict 84. But if we did this reaction, I'm going to erase some stuff.
This sort of pertains to what you said, I forget where it was on Friday, right? Where for the EE questions, you can either it can either be the same or it can be 0, right?
Right, okay, so I did that. Yeah, there is another option. So let's do this same reaction, like the same molecules. Same molecule, I should say. All right, so if you consider the reaction I just drew on the board, so now it's not cesium thiomethoxide. This is now a neutral sulfur. It's a protic solvent. Protic solvents tend to favor SN1. That sulfur is still a pretty good nucleophile. So we're still going to get really the same product. But now, if this is 90% EE, this will not be, I guess, I'm making diastereomers actually. This will be less than 90% EE over here. All right, so what will happen if it's not so I can't remember who asked the question, but every SN2 interaction, so nucleophile hits an electrophile and does an SN2, that reaction inverts the chiral center. Every SN1, leaving group leaves, you get a planar carbocation, nucleophile comes in, that gives racemization. But, again, we got 10 to the 23rd molecules, right? So nothing says every molecule has to do the same reaction. This molecule, 90% of the molecules could do SN2, but the other 10% would do SN1. And if that happens, right, the 90% that does SN2 is going to invert. The 10% that does SN1 is going to give you 50-50. So what it would look like is 95% of the molecules invert, 5% stay the same. And then if I'd done this, I could have presented